Next, teaching large language models to reason about code execution. A fundamental skill among human developers is the ability to understand and reason about program execution. As an example, a programmer can mentally simulate code execution in natural language to debug and repair code, also known as rubber duck debugging. However, large language models, or LLMs, of code are typically trained on the surface textual form of programs, thus may lack a semantic understanding of how programs execute at runtime. To address this issue, we propose NExT, a method to teach LLMs to inspect the execution traces of programs, or variable states of executed lines, and reason about their runtime behavior through chain-of-thought rationales. Specifically, NExT uses self-training to bootstrap a synthetic training set of execution-aware rationales that lead to correct task solutions, for example, fixed programs, without laborious manual annotation. Experiments on program repair tasks based on MBPP and human eval demonstrate that NExT improves the fix rate of a Palm 2 model by 26.1% and 14.3% absolute, respectively, with significantly improved rationale quality as verified by automated metrics and human raters. Our model can also generalize to scenarios where program traces are absent at test time. 1. Introduction. Recent years have witnessed the burgeoning of large language models, or LLMs, trained on code. While those LLMs achieve impressive performance in assisting developers with writing, editing, explaining, and reviewing code, they still struggle on more complex software engineering tasks that require reasoning about the runtime execution behavior of programs. On the other hand, it is not always sufficient for the model to suggest good code solutions, but it is often necessary to provide an explanation to developers to document what the change does and why it is needed. These explanations can help developers better understand the code solutions from models and make more informative decisions. For example, program repair is the task of fixing bugs in a program. Human developers usually learn to debug and fix code by interacting with code interpreters or debuggers to inspect the variable states of executed lines. Such practice helps them acquire a mental model of program execution so that they could mentally simulate code execution in a more abstract manner using natural language, as in rubber duck debugging. Therefore, a program repair model would be more helpful to developers if the model could carry out similar reasoning about program execution in order to explain bugs to programmers. With this inspiration, our goal is to improve the ability of LLMs to reason about program execution when solving coding tasks. In this paper, we propose naturalized execution tuning, NExT, which aims to teach LLMs to reason with code execution by inspecting program execution traces and reasoning about the code's runtime behavior in natural language. At a general level, for a coding-have task, the main idea is to train a model to generate intermediate NL rationales, as in chain-of-thought reasoning, but to provide the model with a trace of the execution of the program in question, so the rationale can be more accurate and grounded on program semantics. Teaching LLMs to reason about program execution in NL would not only offer better interpretability, it could also increase the diversity of solutions predicted by the model. Figure 1. NExT fine-tunes an LLM to naturalize execution traces into the chain-of-thought rationales for solving coding tasks. It performs iterative self-training from weak supervision by learning from samples that lead to correct task solutions. Fig 1 illustrates our proposed approach when applied to program repair. Given an NL task instruction X in Fig 1 and a buggy program Y, as well as the execution traces of the program E, an LLM solves the task, e.g., predict the fixed code Y using chain-of-thought (COT) reasoning to generate a natural language rationale, R, leveraging the execution information 1. Intuitively, program traces encode useful debugging information such as line-by-line variable states, e.g. the value of star list in EPR, Fig 1, or any exceptions thrown, which could be useful for LLMs to identify and fix bugs by reasoning over the expected and the actual execution results, e.g. highlighted text in R. To help LLMs understand execution traces, NExT represent traces as compact inline code comments, e.g. 1, star list equals in F, more in Faker 3, without interrupting the original program structure. While execution traces capture informative runtime behavior, we find it challenging for LLMS to effectively leverage them out of box through COT prompting. Therefore, we opt to fine-tune LLMS on high-quality COT rationales that reason about program execution. NExT uses weakly supervised self-training to bootstrap a synthetic training set by sampling rationales that lead to correct task solutions verified by unit tests. Using unit tests as weak supervision, NExT learns to discover task-specific, execution-aware NL rationales without relying on laborious manual annotation of rationales. NExT executes this self-training loop for multiple iterations, solving more challenging tasks with improved success rate and rationale quality. While there are a variety of types of execution information that we may provide to an LLM, in this work, we limit the execution information to program states and variable values from the execution trace, which is common information that human developers also use. Figure 2. NExT represents execution trace as inline comments. More details in Section 2 and Appendix A1. We evaluate NExT with the Palm 2L model on 2 Python program repair tasks. Experiments show that NExT significantly improves Palm 2's ability to reason about program execution in natural language, improving the program fix rate on MBPP-R by 26.1% and Human EvalFix Plus by 14.3% absolute, respectively. When compared against a strong self-training program repair approach without predicting NL rationales, our model achieves comparable accuracy with significantly improved sample diversity. Interestingly, while our model learns to reason with pre-existing execution information in input program traces, it also generalizes to the out-of-distribution scenario, where execution traces are not available at test time. Finally, to measure the quality of model-generated rationales, we propose a proxy-based evaluation approach, which approximates rationale quality using the performance of smaller LLMS when prompted to solve the original task following those rationales from our models. Through both proxy-based evaluation and human annotation, we demonstrate that NExT produces helpful NL rationales which explain the causes of bugs while suggesting potential fixes. The generated rationales are of significantly higher quality compared to those from the base Palm 2L model. 2. Task: Program repair with traces. Here we introduce our task of program repair with execution traces using chain-of-thought reasoning. Program repair with execution traces. As in Figure 1, given an instruction X and a buggy code solution Y hat, automated program repair aims to generate a fixed program Y hat such that Y hat passes all test cases tau in an executor epsilon, that is, epsilon of Y hat, tau equals 1, while epsilon of Y bar tau equals 0. In this paper, we focus on the task of program repair using execution traces. Specifically, a program trace is a sequence of intermediate variable states after executing each statement in Y hat against a test case tau. Intuitively, traces record the computation of a program and can provide useful debugging information, for example, exceptions to repair Y hat. To use LLMS to repair programs with traces, we concatenate the task instruction, the buggy code, the test cases, and their execution traces as a prompt. To help LLMS understand program traces, we design a prompt-friendly trace representation by formatting epsilon as compact inline code comments, that is, E in Figure 1, as discussed later. Co-T reasoning with execution. We focus on using chain-of-thought reasoning to solve program repair problems by reasoning with execution, where an LLM is prompted to generate an NL rationale R together with a fixed program Y, as in Figure 1. Specifically, we consider rationales that contain reasoning steps to identify and explain bugs in the original code, for example, the second paragraph in R, Figure 1, as well as suggestions to fix the buggy code, for example, a fixed version that uses re.findAll. Since rationales are generated using traces, they often include useful reasoning about program execution that helps localize the bug, such as identifying a counterfactual between the expected and the actual variable values of a statement, for example, the highlighted text in R. Table 1. Few-shot prompting repair accuracy using greedy decoding. Results worse than the previous row above them are underlined in red. Explanations can be helpful for developers to understand bugs in the original code and the model's fixed solutions. Kang et al., 2023. We therefore aim to improve the quality of NL rationales along with the fix rate by teaching LLMs to reason with execution information. An LLM-friendly trace representation. The raw execution traces collected at runtime contain complete variable states for each executed statement, Pot 2. Encoding all such information in prompts is not feasible given the context limit and computation overhead of LLMs. To address this issue and make execution information more intelligible to LLMs, we propose an inline trace representation format, which encodes variable states as inline comments of the traced program. Fig 2 shows an example. Specifically, each inline comment only encodes changed variables after executing that line. Because statements may be invoked multiple times in non-obvious orders, e.g. in loops like lines 4 to 8 in Fig 2, we index the variable states based on the execution order, e.g. 3n equals 1 and 4 even list equals 1, and one may reconstruct the original execution footprint by following those variable states in order. We further compress the trace information for loops by omitting the variable states in intermediate iterations, e.g. in lines 4, 6, and 8. Intuitively, by showing states as pseudo-comments within the original code without interrupting the program structure, our trace representation is significantly more compact than existing approaches that unroll executed lines of code and pair them with line-by-line variable states, while allowing an LLM to leverage its learned code representation to understand the additional execution effect of each statement. Implementation details about handling complex control structures are discussed in Appendix A.1. 3. Preliminary study. Can LLMs reason with program traces in natural language? Before introducing NExT, we first conduct a preliminary study to explore whether LLMs could reason with execution traces in natural language out of the box without additional training. Answering this question will motivate our fine-tuning approach to improve such reasoning skills. Specifically, we follow the trace representation in Section 2 and few-shot prompt in LM to solve program repair tasks using CoT reasoning. Models. We evaluate the following general-purpose models: Palm 2L, GPT-3.5, GPT-4, and Mixtral. We also test two code-specific LLMs, StarCoder and DeepSeek Coder. Tab 1 reports the results on two Python program repair datasets. Language models struggle on chain-of-thought reasoning with traces. We observed mixed results when comparing vanilla prompting with traces without chain-of-thought in Table 1 and chain-of-thought prompting with rationales. Surprisingly, chain-of-thought prompting is even worse on Human Eval Fix Plus, with an average drop of negative 7.8% compared to vanilla prompting, especially for code-specific language models, 57.3 to 30.5 for DeepSeek Coder, and 29.3 to 16.5 for StarCoder. After inspecting sampled rationales predicted by Palm 2L, we observed that the model is subject to strong hallucination issues, such as mentioning exceptions not reflected in the given traces. Indeed, as we later show in Section 5.2, the overall correctness rate of explaining errors in input programs among these sampled rationales from Palm 2L is only around 30%. Moreover, chain-of-thought reasoning is even more challenging for those models when we remove execution traces from the inputs, plus chain-of-thought minus trace, resulting in an average performance drop of 4.8% on MBPPR and 4.3% on Human Eval Fix Plus. These results suggest that while our trace representation is useful for language models to understand and leverage execution information for program repair, since minus trace leads to worse results, they could still fall short on chain-of-thought reasoning using natural language without those program traces. This finding therefore motivates us to improve language models in reasoning with execution through fine-tuning, which we elaborate in Section 4. Section 4. Next, naturalized execution tuning. We present NExT, a self-training method to fine-tune language models to reason with program execution using synthetic rationales. Overview of NExT. Figure 1 illustrates NExT with its algorithm detailed in Algorithm 1. NExT is based on existing self-trained reasoning approaches including Uesado et al. 2022 and Zelikman et al. 2022, which employ expert iteration to improve a base language model using synthetic rationales sampled from the model. Given a training set D of repair tasks with execution traces, NExT first samples candidate natural language rationales and fixed code solutions from the language model. Those candidate solutions are filtered using unit test execution diagnostics, and those that pass all test cases are then used to update the model via fine-tuning. This sample filter train loop is performed for multiple iterations, improving the model's rationales and repair success rate after each iteration. Sampling rationales and code solutions. For each iteration I, we sample rationales R and fixes Y hat in tandem from the current model P theta I, line 5, algorithm 1. We use few-shot prompting in section 3 when I equals 0 and zero-shot prompting with trained models for later iterations. In contrast to existing self-training methods that leverage all training problems, NExT only samples candidate solutions from the subset of problems in D that are challenging for the base model P theta 0 to solve, line 1. Specifically, given a metric M, we only use problems D is a member of D if P theta 0's metric on D is below a threshold M. Refer to Section 5 for more details about the M and M of our program repair task. Focusing on sampling solutions from those hard problems not only significantly reduces sampling cost, it also improves program repair accuracy, as it helps the model towards learning to solve more challenging problems. See Appendix C for more detailed analysis. Filtering candidate solutions. Given a candidate set of sampled natural language rationales and their code fixes, NExT uses unit test execution results to identify plausible rationales that lead to correct fixes for learning, line 6. Using test execution diagnostics as a binary reward function is natural for program repair tasks, since each repair problem in our dataset comes with unit tests to test the functional correctness of its proposed fixes, according to Ye et al., 2022. While we remark that this filtering criteria does not directly consider rationale quality, we empirically demonstrate in Section 5 that the quality of rationales improves as learning continues. Algorithm 1. Naturalized execution tuning. NExT. See formulas. Model training. After collecting a set of training examples script upper B superscript left parenthesis I right parenthesis, we fine-tune the model to maximize the probability of generating the target rationales and code fixes given the task input, line 8. Following Seligman et al., 2022, we always fine-tune the model from its initial checkpoint, P subscript theta 0, to avoid overfitting to instances sampled from early iterations that are potentially of lower quality. Discussion. NExT can be seen as an instantiation of the rationale bootstrapping method proposed in Seligman et al., 2022, section 3.1, which synthesizes latent rationales with correct answers for math and logical reasoning tasks. However, NExT focuses on program comprehension by reasoning with execution traces, which is critical for solving challenging coding tasks that require understanding execution information, such as program repair, section 5. Besides, NExT models both rationales and programs, code fixes, as latent variables. Using unit test execution results as weak supervision, NExT is able to explore possible strategies to reason with execution and discover plausible rationales catered towards solving the specific downstream task. As we show in Appendix D, rationales generated by NExT employ a variety of reasoning patterns to locate and explain bugs in our repair dataset. Finally, while we apply NExT to program repair, our framework is general and can be extended to other programming tasks that require reasoning about execution, such as code generation with partial execution contexts, Yin et al., 2023, or inferring program execution results, Nye et al., 2021, which we leave as important future work. Section 5. Experiments. Models. We evaluate NExT using Palm 2L Unicorn as the base LLM, Anil et al., 2023. Its fine-tuning API is publicly accessible on Google Cloud Vertex AI platform. Datasets. We use two Python program repair benchmarks, MBPPR and Human EvalFix Plus, eFix Plus hereafter. MBPPR is a new repair benchmark that we create from MBPP, Austin et al., 2021, a popular function-level Python code generation dataset. We create MBPPR by collecting LLM-generated incorrect code solutions to MBPP problems, with a total of 10,047 repair tasks for training and 1,468 tasks from a disjoint set of MBPP problems in the development for evaluation, Appendix B1. In addition to MBPPR, we also evaluate on eFix Plus. HeFix Plus is derived from Human Eval Fix, Munikoff et al. 2023, which consists of 164 buggy programs for problems in the Human Eval dataset, Chen et al. 2021a. We further augment Human Eval Fix with the more rigorous test suites from Eval Plus, Liu et al. 2023, to obtain HeFix Plus. While both original datasets, MBPP and Human Eval, feature function-level algorithmic code generation, Table 2, improvements by NExT on the PaLM 2.5 model. In subscripts on MBPPR, GPT 3.54 results are for reference. Figure 3, greedy decoding results on MBPPR on PaLM 2L plus NExT and existing LLMs. Problems from the two datasets may still differ in their topics, algorithms, or data structures used. Therefore, we use HeFix Plus to measure generalization ability without further fine-tuning. Evaluating code fixes. We use pass at k, defined as the fraction of solved repair tasks using k samples, k less than or equal to 25, to measure the end-to-end functional correctness of fixed programs with tests. Evaluating rationale quality. Decoupling the quality of intermediate CoT rationales and downstream task performance. Program repair pass at k is a non-trivial research question in LLM reasoning. What, with most works on improving CoT reasoning, still hill climbing towards downstream task performance without evaluating intermediate rational quality. To disentangle the evaluation of rationale quality from end-to-end repair accuracy, we propose an extrinsic proxy-based evaluation metric for rationales. Specifically, given a rationale R, we prompt a smaller LLM to solve the original repair task conditioning on R, and use the correctness of the predicted code fix using greedy decoding to approximate the quality of R. Intuitively, smaller LLMs would rely more on information from the rationale and could be more sensitive to its errors. Therefore, their performance could be a better indicator of rationale quality. We report average scores on two PaLM 2 variants for proxy-based evaluation. 1, a smaller general-purpose language model, PaLM 2S, and 2, PaLM 2S star, which is specialized in coding. Note that while we primarily use proxy-based metrics to evaluate rationales, we also perform human ratings of rationale quality with results in line with our proxy-based evaluation. Hyperparameters. We perform temperature sampling, t equals 0.8, with a sample size of 32 for training, S subscript j equals 32 in algorithm 1, and pass at k evaluation. In the first iteration in algorithm 1, we use pass at 1 estimated with these 32 samples as the filtering metric m dot to find challenging problems whose m dot is less than 10% for training. We perform 10 iterations of NExT training and pick the best model using pass at 1 on the development set. Figure 4. Ablations on removing rationales and/or traces during the iterative training of NExT. Note that different min and max values are taken for y-axis for clarity among different curves, but consistent gridline intervals are used for easier comparison. 5.1. Main results. In our experiments, we compare our model with strong LLMs used in Section 3, analyze the impact of rationales and program traces, and perform generalization experiments on HeFix Plus and human evaluation of rationale quality. NExT improves program fix rate. We first compare the end-to-end program repair performance of PaLM 2L before and after NExT training, PaLM 2L plus NExT in Table 2. Left, NExT leads to significant improvements on the end-to-end fix rates across the board, with a 26.1% absolute improvement on pass at 1. Interestingly, the gain on pass at k is generally higher for smaller k. This might suggest that the model becomes more confident about program fixes after NExT training, while the sample diversity also improves, as indicated by improved pass at 25. For reference, we also include results from GPT models. Notably, PaLM 2L plus NExT outperforms GPT 3.5 on all pass at k metrics. NExT improves rationale quality. Table 2 right shows the improvements of PaLM 2L plus NExT on our proxy-based evaluation, where we approximate rationale quality using the performance of smaller LLMs when conditioned on those rationales. Again, NExT yields consistent improvements across all pass at k metrics. This suggests that NExT improves PaLM 2L's skill in reasoning with execution to solve MBPPR problems, leading to rationales that are more helpful for smaller LLMs. In Appendix D, we present a case study to demonstrate different reasoning strategies PaLM 2L plus NExT adopts to repair programs using execution information. As we later show in Section 5.2, Our proxy-based metrics are also consistent with human ratings, and rationales from Palm 2L plus NExT are strongly preferred by annotators compared to those from Palm 2L. Palm 2L plus NExT outperforms strong LMs. We compare Palm 2L plus NExT with a series of strong LLMs from the preliminary study section 3 in Figure 3. Palm 2L plus NExT outperforms strong open-source LLMs by a minimum of 29.4% and 11.1% on end-to-end and proxy-based pass-at-1 results respectively, while on par with GPT 3.5. These results show that Palm 2L plus NExT is a competitive model on program repair by reasoning with execution. Learning to reason in natural language improves generalization and sample diversity. To further demonstrate the importance of using code reasoning in NExT self-training, we compare Palm 2L plus NExT with a strong self-training-based program repair model implemented in NExT, which directly generates code fixes using runtime execution information without caught reasoning. This ablation resembles self-APR, which also adopts self-training to iteratively synthesize data using unit test diagnostics, while our ablation uses traces with richer execution information. Figure 4 shows model performance DUT NExT training iterations. When trained without caught reasoning, NExT, Table 3, Palm 2L plus NExT trained with traces outperforms Palm 2L when traces are absent at test time as shown in highlighted results. Results are on MBBPR. Test with trace results from Table 2. Without rationale, Palm 2L converges much faster on the training set, which is not surprising since the model only learns to generate code fixes without additional reasoning tasks such as explaining bugs in natural language. However, on the development set, Palm 2L plus NExT still outperforms this baseline in pass-at-10 with comparable pass-at-1 accuracy, and the gap on pass-at-10 becomes larger with more iterations. This shows that by reasoning in natural language, Palm 2L plus NExT generalizes much better to unseen MBBPR problems with greater sample diversity. In Figure 6 of Appendix C, we also show that the gain from Palm 2L plus NExT against this ablation on pass-at-K is even more pronounced for larger K greater than 10, which suggests that learning to reason in chain-of-thought rationales improves sample diversity on program repair, similar to the findings on other code generation tasks. Reasoning with execution traces is critical. To understand the importance of leveraging program traces to reason with execution, we compare with an ablation of NExT without using program traces, which follows the same procedure in Algorithm 1, except that traces are not used to generate rationales in line 5, NExT without traces. This variant can also be seen as a direct application of the rationale generation bootstrapping method in Seligman et al., which trains a model on sampled rationales that lead to correct task solutions without relying on additional execution information. Without traces, Palm 2L plus NExT is consistently worse than Palm 2L plus NExT on the development set across iterations, both in terms of end-to-end fix rate and proxy-based metrics. This suggests that reasoning with execution information is critical for Palm 2L on program repair tasks. Interestingly, while the gap on the development set is significant, the two models achieve similar scores on the training set, which suggests that reasoning with pre-existing execution traces also help the model generalize better to unseen tasks at test time. Our model works without traces at test time. While program traces are crucial for reasoning with execution, such execution information may not always be available at test time, for example, when execution is prohibitively expensive. To stress test Palm 2L plus NExT in scenarios where execution information is absent, we remove execution traces from its input at test time in Table 3. Palm 2L plus NExT still yields an end-to-end fix rate of 40.8%, which is an 21.8 improvement over the 3-shot Palm 2L baseline and is only 3.3 lower than NExT trained without traces, for which is tested in distribution. The results from the proxy-based evaluation of rationales are also consistent with the fix rate. Our model generalizes to HEFIX plus at test time. To further evaluate the generalization ability of Palm 2L plus NExT, we test our model trained on MBBPR on HEFIX plus. Table 4 summarizes the results. NExT achieves reasonable generalization on HEFIX+, outperforming the base Palm 2L model by a large margin, that is, 14.3% on end-to-end fix rate and 6.0% on proxy evaluation. Aligned with our previous findings on MBBPR in Figure 4, reasoning with execution traces, comparing without or with traces, improves fix rate and rationale quality. Moreover, we remark that with iterative learning, Palm 2L plus NExT is on par with the strong program repair method without chain of thought reasoning, that is, without rationale, similar to the results on MBBPR. This is in contrast with our preliminary study in Section 3, where Palm 2L with chain of thought prompting is much worse than vanilla prompting without using rationales. Overall, these results indicate that Palm 2L plus NExT could robustly generalize to out-of-distribution repair tasks. Table 4. Generalization results on HEFIX+. Palm 2L plus NExT models are only trained with MBPPR, obtained using greedy decoding, no traces provided at test time. Table 5. Results for human annotation of rationale quality. Base models use three-shot prompting. Numbers under the questions are counts of ratings without additional dataset-specific fine-tuning. 5.2. Human evaluation of rationale quality. Our proxy-based evaluation suggests the extrinsic value of the COT rationales from Palm 2L plus NExT. We further conduct an intrinsic evaluation by manually rating the quality of model-predicted rationales on 104 sampled MBPPR repair tasks from the dev set. Specifically, we ask raters to judge the quality of rationales generated by three models, Palm 2L plus NExT, Palm 2L, and GPT 3.5, in a three-way side-by-side setting. Each rationale is rated in two aspects. 1. Its helpfulness in explaining bugs, Question 1, first two paragraphs in F, Fig 1, and 2. Its helpfulness in suggesting code fixes, Question 2, e.g., a fixed version that uses ... in F. Each question has a three-scale answer, completely correct and very helpful, partially correct with minor errors but still helpful, incorrect and not helpful. We also compute an overall score of rationale quality using numeric values of +1, 0.5, 0 for the three scales, and averaged over Question 1 and Question 2. Finally, we ask raters to pick a single best choice if there is not a clear tie. More details about our human evaluation pipeline is described in Appendix B. 3. Tab 5 summarizes the result. Compared to the base Palm 2 model, Palm 2L plus NExT generates significantly more high-quality rationales with correct explanations of bugs and fix suggestions. Additionally, compared to GPT 3.5, Palm 2L plus NExT also has more rationales with correct bug explanations. While interestingly, GPT 3.5 generates more rationales with partially correct fix suggestions. We hypothesize that including more exemplars with detailed fix suggestions to our few-shot prompts during NExT training, Appendix E, would help mitigate this issue. Nevertheless, the overall scores and rater-assigned best choice suggest that the rationales predicted by Palm 2L plus NExT are of significantly higher quality compared to those from Palm 2L, and are on par with the predictions from GPT 3.5. Overall, this finding is in line with the proxy evaluation results in Fig 3. GPT 3.5, Palm 2L plus NExT Palm 2L, suggesting that the latter is a reasonable surrogate metric for rationale quality. In Appendix D, we present example-generated rationales that show a variety of reasoning patterns. 6. Related work. Reasoning about program execution. Several lines of research have explored learning methods to reason about program execution. Program synthesis systems often leverage the execution states of partially generated programs to guide search in sequence-to-sequence models. There has also been work on training neural networks to mimic program execution, like a learned interpreter, often with specialized neural architectures to model the data flow of program execution. Instead of using domain-specific architectures to encode and reason about program execution, our work focuses on teaching large language models to reason with execution in natural language. In particular, Scratchpad and self-debugging are two notable works that also model execution traces using LLMs. The core difference is that these methods focus on predicting reasoning chains that contain trace information, such as executed lines with variable states or their natural language summaries. On the other hand, NExT aims to leverage existing execution traces from a runtime to aid the reasoning process, which often leads to more compact rationales tailored for downstream tasks. We present a more detailed comparison and discussion on NExT and these related works in Appendix A, Point 3. Program repair. Several works in program repair have leveraged execution information such as traces or test diagnostics. Different from a study which represents traces by directly pairing unrolled executed lines with their variable states, NExT inlines indexed variable states as code comments, which is more token efficient while preserving the original code structure. Similar to NExT, another work constructs synthetic self-training data using test execution results, while our approach generates both natural language rationales and fixed programs with better interpretability. Recently, large language models have been applied to program repair. Among them, another study uses a React-style chain-of-thought reasoning loop to predict repair actions based on interactive feedback from debuggers, while NExT focuses on tuning large language models to reason with pre-existing execution information without intermediate feedback. Finally, as a related stream of research, self-improvement methods iteratively refine a model's code solutions using chain-of-thought reasoning over self-provided or test-driven feedback. Instead of relying on high-level execution signals like error messages, NExT trains large language models to reason with stepwise program traces. Our learnable rationales are also more flexible without following a predefined reasoning template. Besides, since traces already capture rich execution semantics, the resulting rationales could be more succinct and targeted to the downstream task, for example, explain bugs, without redundant reasoning steps to trace the program by the model itself to recover useful execution information. Supervised CoT reasoning. Large language models can solve problems more accurately when instructed to work out the answer step by step in a chain of thought or a scratchpad. Improvements on this approach involve fine-tuning large language models on chain-of-thought reasoning data. Such chain-of-thought data is either manually curated or distilled from more capable teacher models. Instead of relying on labeled or distilled data, NExT uses self-training to iteratively bootstrap a synthetic dataset of high-quality rationales with minimal manual annotation. Our work differs from previous work using bootstrapping in the type of rationales and the use of execution information. See Tracker 4 for more discussion. While we use the correctness of the program fix for filtering the rationales, which is reminiscent of outcome supervision, it is also possible to use process supervision with human annotations, or obtain such supervision automatically by estimating the quality of each step using Monte Carlo tree search and by identifying partially correct program prefixes. Finally, existing research has investigated fine-tuning of LLMs to predict the execution information directly, such as predicting line-by-line execution traces, abstract runtime properties, or final output. NExT addresses a different problem. Instead of predicting the execution information, NExT takes it as given and instead learns to discover flexible task-specific NL rationales that aid a downstream programming task. 7. Conclusion. In this paper, we present NExT, a self-training method to fine-tune LLMs to reason with program execution given traces. We demonstrate that Palm 2L trained using NExT yields high-quality natural language rationales and achieves stronger success rates on 2 program repair tasks. As future work, we plan to apply NExT to a broader range of program understanding tasks while expanding the trace representation to support more programming languages. This concludes the reading of NExT, Teaching Large Language Models to Reason About Code Execution on Research to You. If you would like more papers added, please leave a comment. If you would like to be notified when more papers are available, be sure to subscribe, like, and ring the bell.